I have this question, blah, 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 okay? We are not many in this course, so there is no problem to make it more interactive. You can ask questions, interrupt, and all this. It's possible to record the lectures. I've seen last time there was a question about this. No problem. You can you can record each meeting. The only thing is that all these lectures and the materials are property of the University of Palermo. So I ask you not to redistribute outside the university and not to copy the materials and distribute them to other people. Okay.
Sure.
So all this material is just for the purpose of these lectures, and it should not be used outside for any purpose. Okay.
Sure.
Okay. So are there any questions or comments about the last lecture? Did you have time to look back to the Fourier transform and Laplace transforms?
No, sir.
Did you? Okay. Okay, so now let's start the course, since last time was just a brief introduction. And let me share the screen with the presentation. Okay. So let me share presentation. Okay, so do you see the presentation? I don't hear you. Do you see the presentation?
Yes, sir, you can see the presentation.
Okay. Okay, so let's go back on a wider introduction about signal processing. It is true that we as humans are actually some advanced signal processors, because every time we speak, we see, we hear, basically we are processing some signals that we are able to recognize, and we are modulating signals when we are speaking. Okay? And we encounter in our lives many types of signals in several applications. For example, we have electric signals, if you think about voltage, magnetic and electric field, and so on. Mechanical signals, such as velocity, force, displacements. Acoustic signals, sound, vibration, and other signals like pressure and temperature. And most of these signals that we encounter in the real world are analog signals, not digital. Okay? And analog signals are often continuous in time and in amplitude. So when we convert voltage, for example, to current, what we use is that we use sensor or transducers that change analog signal in another analog signal. Okay? If we have analog circuits or analog filters, these filters are used, are changed or manipulated using resistors, capacitor, inductors, amplified, and so on. And for example, when we have analog signals like FM radio or traditional TVs, this is audio and video signal processing of these analog signals. Okay. What are the limits of the analog signal processing, and why we study digital signal processing? First, there is a problem of accuracy, because analog circuits are often nonlinear. And second, there is often strong ambient noise. Also, these analog signals and these environments constitute a limited repeatability because the environment conditions change all the time. For example, the temperature changes, and therefore also the processing performance changes as well. There's a limited dynamic range in the circuits for voltage and currents, for example. And also it's difficult to implement certain operations like non-linear or time-varying operations. This is very difficult or impossible to do in analog signal processing. And also storing information is difficult in analog circuits. So in digital signal processing, what we do is that we represent signals as sequence of numbers. And often we do some sampling or analog to digital conversion, because since all these signals from the real world are analog, then we need a signal processing or a sampling or analog to digital conversion in order to do the digital signal processing. Then what we do is that we have the digital signal and we process this signal using a digital processor. This is why we call it digital signal processing. And then once we have done the digital signal processing, we want to go back often to the real world. And in the real world, as we said, the signals are analog. So we reconstruct the analog signal after the digital signal processing using the digital to analog conversion. Okay, so this what you see here at the bottom is the chain from the analog signal back to the manipulated analog signal, but going through the digital signal processing. So you have the analog to digital conversion, the signal processing, and then again the digital to analog processing. Okay. Now in this course, we will not deal on this type of conversions. We will just focus on the digital signal processing and how to perform signal processing on digital signals. Okay. So what are the pros and cons of digital signal processing? The advantage is for sure the accuracy, because depending on the word length or using floating point numbers, we can extend the accuracy almost indefinitely. And the dynamic range can be controlled very precisely. Also, the digital signal processing is repeatable. If you use the same input sequence, the output sequence will be always the same when you use the same digital signal processing. Because sensitivity to electrical noise is minimal, and the software implementation is very flexible. You can change it easily without having to rebuild the entire circuit. It is also easier to implement nonlinear or time-varying operations. And digital storage is very, very inexpensive. Okay? It can also be encrypted for security, and the price and the performance is very interesting. There is a very short time to market. Okay? Now, the cons of digital signal processing are often tied to the analog to digital and digital to analog conversion, because because the sampling causes loss of information. And for the conversion, you need mixed signal hardware to go from the analog to the digital and vice versa. And also compared to the analog circuits, digital signal processing is very slow. Okay. And also there is some errors due to quantization and round-off when you sample the signals, the signal magnitude, the extension of the samples. Okay. Are there any questions up to now or comments?
No, sir.
Okay. So what are the signal types that you can see? So continuous signals or analog signals are, of course, time continuous signals and can be analog in the sense that it is continuous also the space or the values that they can have, or they can be quantized. Discrete signals are discrete, of course, in time, and then we can distinguish numerical or digital signals. And the reason again is that numerical signals are discrete signals, but can have any value, and instead digital signals are restricted to certain quantized values. For example, as we said, analog signals are voltage, current, and temperature. A digital signal is the attendance of this class, how many people are attending today and the next lecture. And numerical signals are still discrete time, but for example, if we sample every hour the temperature in the room, then this value is numerical because it's a continuous value. It's a numerical value. Okay. So there is this slight difference between these analog or quantized, numerical or digital signals. The sampling operation is a continuous to discrete time conversion. Basically, you have a continuous time signal, and in certain points in time, you take the value. Most of the sampling is periodic. For example, if capital T is the sampling period in seconds, usually capital T is constant. But it's not necessarily true. And the inverse of capital T, 1 over T, is the sampling frequency that is usually measured in hertz. You can also indicate the sampling frequency in radian per second. In this case, we indicate the sampling frequency as omega, and it's equal to 2 pi the frequency sample, fs. Okay, is it clear? So if we consider the continuous signal xc, and if we use the periodic sampling, then the sequence x of n of the samples is equal to xc with xc in the points of n times capital T, for n that goes from minus infinity to plus infinity. This is what you have seen here in the center. Okay? Now, there is a problem with sampling, either periodic or not, is that sampling in general is not reversible. We are losing information when we are sampling. For example, if we consider here the samples every 20, here there's no time, let's say 20 seconds. Let's suppose that these are seconds. So here you have samples or on +1 and -1 every 20 seconds. But in these points, you can fit several curves. You can fit the green curve, which is basically square wave. You can also fit the red curve, which is a triangular wave. And you can also fit the blue curve, which is a sine wave, or cosine wave, or a sinusoidal wave in general. Okay? So if we have these samples, +1 and -1, which was the signal that we have sampled? We don't know. We cannot reconstruct the original signal. We have lost this information. However, under certain specific conditions, we can precisely reconstruct the analog signal from the samples without any loss of information. Okay? And we will see how and why in this lecture. So, discrete time signals are basically a sequence of numbers. And generally, they come from sampling a continuous time signal. So, here we have the example of a signal. And just below are the samples of the signal. And basically, in this operation, you have the sequence, but you have somehow lost the information on time. Okay? So this, if we know the sampling period, then we can reconstruct. But in principle, discrete time signals are just a sequence of numbers where there is no information on time. We can define causal sequences and systems where a causal sequence is 0 for n negative. So basically a causal sequence is 0 until the 0 instant, and then it's different than 0. An anti-causal system is just the opposite. It's 0 for n that is 0 or greater than 0. And we will see that this has some implication. For example, a system that is causal has an output function that is only function of the present and previous samples. For example, the backward difference is a causal system because it depends only on the past. In this case, we have y of n that is equal to x of n minus x of n minus 1. So it depends only on the present and the past instance or samples. The forward difference is an anti-causal system because it depends on the sample of x of n, but also on the future sample x of n plus 1. Okay? Now let's see some basic sequences and operations. The first operation is the delay or the shift in time of a sequence. And I will use two types of notations here and in the lecture notes for simplicity. Sometimes I use y of n equal to x of n minus n0 with the square parenthesis, or sometimes with the round parenthesis, or sometimes without the parenthesis like you have here on the right. Okay? It's the same. It's just a matter of notation. And some basic sequences that are important are the unit sample or impulse sequence, which is basically 0 always, except for n equals 0. And we use call it as delta of n, similar to the Dirac delta in the continuous time. The only difference here is that there is no mathematical complications, because for n equals 0, delta is equal to 1. Okay? So this is, from a mathematical point of view, is much simpler than the Dirac delta. Another important sequence is the unit step sequence, which is 0 for n negative, and 1 for n greater or equal than 0. Okay? Now, if I ask you, is the unit step sequence a causal sequence or an anti-causal sequence, what would be your answer? U of n, is it causal or anti-causal? Yes, it's a causal sequence, because it's 0 for n negative. Another important category of sequences is the exponential sequence. Now, this that you see here is a real exponential, but we will often see complex exponentials. Okay? Let's see now the class of sinusoidal sequences. Now, if you consider the sequence of x of n cosine of omega 0 of n plus p, you can also see this as, you can also represent this as complex exponentials. So if we have a complex alpha with a magnitude of alpha and a phase omega 0, and a complex constant a with magnitude a and phase phi, then you can represent the complex exponential x of n equal to a alpha to the power of n. And this can be developed with the definitions that we have written before. So we have that x of n is equal to the magnitude of a times the magnitude of alpha to the power of n times e to the power of j times omega 0 n plus phi. So basically this is a complex number. And this can also be represented with cosine and sine components, so real and imaginary components, as the magnitude that is always magnitude of a and magnitude of alpha to the power of n, and then the real component cosine of omega 0 n plus phi, and the imaginary component, which is j sine of omega 0 n plus phi. Okay? Is it clear to everybody? You have experience with the complex numbers?
Yes, sir.
It should be quite straightforward, right? Now, there is an important difference from the continuous time complex exponentials and the discrete time complex exponential. Because when you have discrete time, there is an ambiguity of 2 pi in the frequency. So every time you have a sum of 2 pi k times n, basically you obtain again the same value. So the first thing is that complex exponential in the discrete time are periodic. And the second thing is that the discrete time sinusoids are not necessarily periodic in 2 pi over omega 0. So cosine of omega 0 n plus phi is equal to cosine of omega 0 n plus omega 0 capital N plus phi only if n as 2 pi k divided by omega 0 is an integer. Okay? So if you have this property that is an integer when you add 2 pi k divided by omega 0, then the sinusoid is periodic, but in general it's not periodic. Okay, I don't know if this is clear. So discrete time sinusoids in general are not periodic. Okay? And plus there is an ambiguity on the frequency. So it's a bit tricky when you treat sinusoids in discrete time. Okay? Is it clear for everybody?
Yes, sir.
Okay. Now, last thing before having maybe a short break is the representation of sampling. It is convenient to represent the sampling operation in 2 stages. The first is an input train modulator. So we multiply the continuous signal with some deltas, with a train of impulses. Okay? And after, what we obtain is just the train of impulse signals modulated with the continuous signal. And then we convert the impulse train in a sequence of numbers. So we convert, and often we quantize the values of these train of impulses modulated by the continuous signal in numeric numbers, in numeric sequences. Okay? The digital sequences, that is X of n. And then from there on, we have the discrete sequence on which we do the signal processing operations. Okay? Okay, so let's have 5 minutes break, and then we will continue our lecture. Okay? Are there any questions up to now?
Sure.
So in 5 minutes we will continue.
Okay.
Okay, so let's continue. And let me share again the screen. Okay. So let me give you let's say an overview of the different Fourier transforms, some of which I assume that you already know, and some of which are new for you. You have probably studied in previous courses Fourier series and the Fourier transform. The Fourier series are defined for continuous periodic signals, and in the frequency domain you have an infinite number of coefficients. So you have the Fourier coefficients that define the Fourier series. So a discrete infinite number of coefficients. That is the Fourier series representation of a continuous periodic signal. The Fourier transform instead is defined for a continuous infinite signal that is not periodic, and the Fourier transform gives us another continuous, in general, gives us another continuous infinite signal or function that is function of the frequency, and we can define as capital X of omega. These two transforms, the Fourier series and the Fourier transform, I assume that you know already from the previous courses. If not, I urge you to study it again, or to study it from scratch if you have never seen it. Is there anybody that have never seen the Fourier series or the Fourier transform in the past from previous courses? Okay, so I will assume that you know these, and although I will give you a little bit of sometimes I will speak about the Fourier transform in the continuous time, but I will not go too much into the details in the properties and in the meaning and so on. Okay. What we will see in this course in a deep way, so we'll study in this course the discrete time Fourier transform, that is abbreviated the DTFT, that transform a discrete infinite sequence x of n in a continuous periodic function x of e to the j omega. And we will see this today, the discrete time Fourier transform, and I will tell you why the DTFT gives us a continuous periodic function from a discrete infinite sequence. Also, we will study the discrete Fourier transform and the discrete Fourier series, which are different from the DTFT because they transform a finite or periodic sequence in the discrete time into a finite or periodic discrete sequence in the transform. that we indicate as capital X of K. So the DTFT transform a discrete infinite sequence in a continuous periodic sequence, and the DFT and DFS transform discrete finite or periodic sequences in discrete finite or periodic sequences. Okay? Let's start, as I said, from the discrete time Fourier transform. Many sequences can be expressed as a weighted sum of complex exponentials as 1 over 2 pi and the integral from minus pi to pi of capital X of e to the j omega times e to the j omega n in the omega. This is the inverse discrete time Fourier transform. The weighting of these complex exponentials is determined by the forward discrete time Fourier transform, which is defined as the infinite summation on n that goes from minus infinity to plus infinity of the sequence elements x of n times another complex exponential that is e to the minus j omega n. Now, capital X of e to the j omega is the Fourier spectrum of the sequence x of n, and it specifies the magnitude and phase of the sequence x of n. Note that the phase wraps every 2 pi. So the phase of the sequence is not unique. Okay? So this is why the DTFT is periodic in 2 pi. We'll see this later better. Let's see first when the DTFT exists. And I will demonstrate that the DTFT exists if, the DTFT exists if the infinite sum converges, so if the definition converges, or in other terms, if the magnitude of the DTFT is bounded for all frequencies. And this means that if we substitute the definition of the DTFT, this means that the infinite sum of x of n e to the minus j omega n, if we take the elements of the summation, must be less or equal of the infinite sum of the magnitude of the sequence elements x of n times the magnitude of the complex exponential e to the minus j omega n. And since the magnitude of e to the minus j omega n is 1, this means that the infinite sum of the absolute of the sequence must be less than infinite, must be bounded. So this is a proof that the DTFT exists if the sequence is absolutely summable. Okay? So if the sequence is absolutely summable, then it will be possible to find or to compute the discrete time Fourier transform. Okay? Now, absolute summability is not a necessary condition to have a DTFT, but only a sufficient condition. Because some sequence might be only square summable, in the sense that they are not absolutely summable, but the summation of the square of the absolute of x of n is less than infinite, is bounded. So to represent sequences that are square summable but not absolutely summable, we can relax the condition of uniform convergence, and we can define the convergence of the DTFT in the mean squared sense. So instead of using the infinite sum, we use the definition of x of n for measuring, let's say, the error, and we want to have a DTFT to exist that the limit of the integral from minus pi to pi of the squared sum of the square magnitude of the DTFT, capital X of e to the j omega, minus capital X of n of e to the j omega is equal to 0. So if this happens, then we can represent the signal with the DTFT. Is it clear? Are there any questions up to now?
Yes, sir.
Yes.
So how do we write limit m approaches to infinity?
I cannot hear you very well. Can you repeat louder?
Yes, sir. I am saying that in the last line you have write limit m approaches to infinity.
Yes.
How can we write this equation?
So basically, this is the condition to have a uniform, so that is not necessarily to have a uniform convergence in the sense that the infinite summation exists. So the definition, let's put it this way. You see the mouse here? When I
Yes.
Okay, so this might not exist, so this might not be bounded. Okay, so the absolute in this case, the absolute condition, the absolute summability is not true, and this condition that we have seen before might not be valid, but maybe this condition here, this one here, might be true. Okay, so this is when I say the convergence in the mean squared sense is this, that maybe this does not exist, but this here might exist. So the difference squared will be equal to 0. Okay.
Okay, sir. What will be the value of m here? It will be an integer or a real number?
Here it's as you can see here is an integer number. Okay, because here we have a sequence, yes, and here m is an integer. Okay.
Okay, sir. Okay. Now I got it. Thank you, sir.
You're welcome. Are there any other questions? Okay. So let's see an example. And the first example I want to show you is the Idle low-pass filter. the ideal low-pass filter has has a magnitude of 1, has the value of 1 in between when omega is in magnitude less than a critical frequency omega c. Otherwise, it's perfectly 0. So the magnitude here, it's shown here on the top of the right. Okay. And if we want to compute the inverse discrete time Fourier transform, we can apply the definition as 1 over 2 pi and the integral from minus pi to pi of the dTft of the low-pass filter, h of HLP of e to the j omega times e to the j omega n in the omega. And this we know because the function h, capital H, of e to the j omega is 1 only from minus omega c to plus omega c. Then we can substitute and we compute the integral only from minus omega c to plus omega c of e to the j omega n in the omega. And this integral, I'm sure you can compute, is equal to 1 divided by 2 pi j n and e to the j omega n in the values of minus omega c and omega c. So basically what you obtain at the end of this is a sort of sinc function in the discrete time, which is sine of omega c n divided by pi n. So the ideal filter, first of all, is not causal, because as you can see, it has values different than 0 for n negative. Here what you see is just an interpolation, because remember that h of n is a sequence, are the samples, okay? But to make it clearer, here you have the continuous function. So since for n negative is different than 0, first of all, the ideal low-pass filter is not a causal system. Okay? Second, it's not absolutely summable. Okay? So we have the DFT, but the sequence is not absolutely summable. And the reason is that we can compute the DFT is that the DFT converges in the mean squared sense, as explained before. Here it's important to note the roles of the Gibbs phenomenon. The Gibbs phenomenon is something that you might have seen in the continuous time. Okay? Here you see some examples of the ideal low-pass filter when you have the error function, let's call it like this, for m that is 1 or greater and so on. So this h of m, you have to think about it as this here, okay? The x of m that is shown here. So when you increase the m, in principle, when n tends to infinity, you have the ideal low-pass filter. But when you have a limited order, so m is a number, you see that there is some oscillations. The magnitude of this oscillation is always the same, but the number of oscillations is different and depends on the order of the ideal filter of this m. Okay? So it's basically impossible to realize an either low-pass filter for these two reasons. First, is not causal, and second, there is the Gibbs phenomenon that gives us some problems. Is it clear for everybody?
I have a question. The Gibbs phenomenon is when you use a low-pass filter despite its form,
So the Gibbs phenomenon is the approximation of the either low-pass filter. When you try to approximate an either low-pass filter, basically the Gibbs phenomenon appears. And in real-world applications, this is important to know. So you cannot do a perfect either low-pass filter. Okay. Also, because here you can see that the impulse response is infinite. Okay. It's so this sort of sinc function that is not causal and infinite. So let's see some properties of the discrete time Fourier transform. Most of these properties are very similar to the properties of Fourier transform in continuous time. And some I will demonstrate. I'll give you a proof later in this lecture or in the next lectures. Probably in this lecture we have time to demonstrate these properties. Here I will not go through all these properties in the details because I will show you more precisely the mathematical proof. But for example, you can see that if you take the conjugate of the sequence, the DTFT is conjugate and there is a swap in the phase. Okay, and basically there is some Hermitian properties. And if the sequence is real, then the DTFT is symmetric and is an even function or conjugate symmetric. If you take the imagery, a sequence that is pure imagery, then what you get is an odd function that is antisymmetric. And vice versa, if you have the sequence that is even or odd, you have a DTFT that is respectively real or imaginary. There are many properties that are of interest for us because most of the signals that we deal with are actually real. And so if a sequence is real, you have that the DTFT is Hermitian, conjugate symmetric. The real part is even and the imaginary part is odd. And also the magnitude is even and the phase is an odd function. Okay? And here are some examples of transformation theorems that are all, that we will see later. I will give you the mathematical proof. Basically, the DTFT is linear, and the delay shift is this multiplication for a phase function. So the delay corresponds to a rotation of the DTFT. And then also what it's interesting for us is that the convolution is in time is the multiplication of the DTFT. This is similar to what happens in the continuous time, where the convolution of continuous functions corresponds to the multiplication of the Fourier transforms. Vice versa, the multiplication of functions in the time domain corresponds to the convolution in the Fourier domain. Okay, this is something you should know also from the continuous time. And here are some examples of Fourier transforms. Some of them, again, we will see during the class. For example, the delta has a transform that is still delta. And here you have shifted delta, which is basically the phase rotation. And interestingly, if you have just a constant function, 1, the dt of t is a delta, but with the ambiguity of the multiple of 2 pi. Okay. For the exponential function, you have, if the magnitude is less than 1, you have that the dt of t is 1 over 1 minus a times e to the power of minus j omega. And for the step function, it's the same, plus the transform of the constant 1. We have seen already the ideal low-pass filter that it corresponds to a sequence of sine of omega c n divided by pi n. And vice versa, if we have a window, a sequence that is 1 only between 0 and capital M, this corresponds to a dt of t that is in the form of sine of omega n plus 1 divided by 2 divided by sine of omega divided by 2 times the phase rotation of e to the minus j omega m divided by 2. And lastly, we have the exponential sequence e to the j omega 0 n that is basically the same of the constant, but with another delay of omega 0. Okay, so let's recall the continuous time Fourier transform that is defined, as you should know already, as I will indicate here xa to say that this is the analog function or the continuous time function. And we have that the continuous time Fourier transform is the integral from minus infinity to plus infinity of x of a of t e to the minus j omega t in the t. Here write big omega to distinguish from the small omega that we use in the discrete time. And the inverse Fourier transform is 1 over 2 pi, and the integral of capital X a of j omega times e to the j omega t in the omega. Now, as I said, that you should remember some important Fourier transform properties, which is that the convolution in time corresponds to the frequency multiplication, and the frequency convolution corresponds to the multiplication in time. And again, the modulation shift is the same as a shift in frequency. Okay, this is somehow similar to the properties of the discrete time Fourier transform. Now, as I said, you can represent sampling as the process of multiplication for a train of impulses, of deltas. Okay, I can show you the slide that I showed before. Basically, we multiply the analog signal xa of t with the sequence of pulse trains of pulses s of t. And here is the if we assume that the periodic the sampling is periodic, then we have the deltas that are shifted by n times capital T. Okay. Now, here on the left, on the top, you have the sampled signal, so the signal multiplied with the pulse trains. And on the right, you have the expression of the pulse train itself, S of t. Okay. If we look at the Fourier transform in the continuous time of both functions, x of s and s, then what we have is that the Fourier transform of the pulse train is still a train of pulses, as you see on the right. And because of the Fourier transform properties, the Fourier transform of the sequence of the signal multiplied with the pulse train is the convolution. The convolution of x of a times s with s, okay? So here you have the expression of this convolution. I will not go too much into the details here, but I want to stress that what we obtain after this multiplication with the pulse train is that in the frequency we have the replication of the original Fourier transform every k omega s. So depending on the frequency sampling, we have the replication of the Fourier spectrum. You will understand this here in this new slide. So we have replicas in the pulse location. So let me explain this graph here that you see, so it's easier to understand. Let's assume that the frequency transform, that the frequency of the original signal, capital X of C, is bounded, is limited between minus omega n and omega n. Okay, so you have this Fourier transform of the original signal, which is just this triangle on top. Okay. Now, if we have periodic sampling of this, what happens is that we have created some replicas at multiples of omega s. So the impulse train modulator replicates the Fourier transform of the input signal, and if we have a sampling frequency which is higher than 2 times the maximum frequency, that is called omega n, or the Nyquist frequency for those that know already, we have that the spectrum does not overlap. These replicas do not sum on each other. Okay, and this is the plot in the center here. Okay, so if omega s is greater than 2 times omega n, there is no aliasing, there is no time overlap, there is no overlap on the frequency, and there is no time aliasing, or frequency aliasing, sorry. Instead, if omega s is smaller than 2 times omega n, what happens is that there is some overlap that actually cannot, that there is some aliasing that does not allow to recover the original signal with low-pass filtering. So the Nyquist sampling theorem tells us that if we have a band-limited signal, so that the frequency transform is 0 for omega greater than the Nyquist frequency omega n, then the analog signal is uniquely determined by its samples. So if the the sampling frequency is greater than 2 omega n, then you can use a low-pass filter to remove the replicas and obtain the frequency transform of the continuous time signal. Is this clear for everybody? Maybe it's something that you have already seen in the previous courses. Okay, the Nyquist sampling theorem. So omega n is called the Nyquist rate, and it's the Nyquist rate is 2 times omega n. Omega n is the Nyquist frequency. The Nyquist rate is the minimum sampling rate in order to not have aliasing, frequency aliasing. So the Nyquist rate is 2 times the Nyquist frequency. Is this clear for everybody?
Yes, sir.
Maybe, as I said, this is something you already know, but in case you don't know, this is something you should have in mind when we go from analog signals to continuous signals. Okay.
Yes, sir.
So let's see more details, the relationship between the continuous time Fourier transform and the discrete time Fourier transform. I will not go through this too deeply because I will show you the complete proof later on. But if we sample the analog function, the analog signal, with a continuous time interval Tc, you can express this with the inverse discrete time Fourier transform, and you can use both the continuous time Fourier transform and the discrete time Fourier transform, and in both cases you have the same sequence x of n. And then maybe I will skip this because I will show you later using the whiteboard. But what you have is that the DTFT, as I said, is the periodic repetition of the Fourier transform. And here is the complete proof of the Whittaker-Nyquist Kotelnikov-Shannon theorem. This is the complete name, but often we call it just the Nyquist theorem or Shannon theorem, that a band-limited signal can be reconstructed from its samples if the sampling frequency is at least double of the maximum signal frequency. And I will skip the proof because you have it in the lecture notes, and I will give you in the whiteboard. I will give you the complete proof, and in any case, you can study it. Actually, I ask you to study it from the lecture notes. Okay, otherwise here we will not have time to do everything. Okay. So again, I will give you 5 minutes break. And then in 5 minutes, I will give you some mathematical proofs of the properties of the DTFT and of the relationship between the Fourier transform and the discrete time Fourier transform. Okay?
Okay, sir.
Okay. So now I will demonstrate, I will give you the proofs of some of the properties that I have shown just on the slides. Okay? Actually, there are. Okay. Schermo intero? No? Anche? Prima galleria. No. Just a second. Sì. Just a second. Galleria in alto, ecco, ho trovato. Galleria in alto. Togli. No, non l'ho fatto. Oh, benissimo. Ok, così deve meglio, no? Okay, so the first property that I want to demonstrate is the linearity of the DTFT. Okay, so let's assume that we have a sequence Z of n, okay, that is the linear combination of k sequences. So for k that goes 1 to capital K, capital N, let's call it, capital N, of a constant lambda of k of x of n, and here we have x of k. So different sequences, x of k, multiplied by constants lambda of k. If we consider the DTFT of the generic sequence x k of n as capital X k of e to the j omega. Okay. Maybe I can make a smaller point about this. Then, if we want to compute the DTFT of Z, so the DTFT of Z, we have capital Z of e to the j omega. That is, let's write first the definition, the summation for n that goes from minus infinity to plus infinity of z of n times e to the minus j omega n. Okay? And we can substitute also here the linear combination that forms z of n, and we have that this is equal of the summation on n of the summation for k that goes from 1 to capital N of lambda k x of k of n. Now this is multiplied by e to the minus j omega n. Okay? So this is equal, if we invert the summations, the order of the summations, we have summation for k that goes from 1 to capital N. And also lambda k does not depend on n, so the constants we can take outside lambda k of the summation for n that goes from minus infinity to plus infinity of x of k of n times e to the minus j omega n. Okay? But each of these elements here are just the definition of the DTFT of the sequence x of k. So we can substitute the summation on k equal 1 to n of lambda k capital X k of e to the j omega. Okay, so I showed you, I gave you the proof that linear combination of, let me highlight it, linear combination of sequences, pretty small, okay, linear combination here corresponds to the linear combination, the same linear combination of the DTFTs. Okay. Okay, so let me give you another proof of the things that we have seen. Regarding the symmetries, we said that well, the symmetries is a bit easy to very easy to demonstrate. Okay, this you can see from, I invite you to see this from the lecture notes, okay? Because it's very easy, so you can study by yourself. I will show you the delay property of the DTFT. So if we consider a sequence x, a sequence x of n, and we consider the delay x of n minus n0, okay? If we compute the DTFT of this, what we have is that is that if we take the DTFT of this, we have the summation for n that goes from minus infinity to plus infinity of x of n minus n0 times e to minus j omega n. And then this means that we have the summation on n of x of n. This is change the variable here, okay? So we have that, let's call it n prime, x of n prime, and I substitute n prime, equal to n minus n0, okay? So we have here the summation on n prime that goes still from minus infinity to plus infinity of x of n prime e to the minus j omega of n plus n0, okay, n prime plus n0, okay? And this you can decompose in the two exponentials. So this factor here is e to the minus j omega n prime times e to the minus j omega n0. Okay, so you can take these bars here outside from the summation, and what is like you have is that this is equal to e to the minus j omega n0 summation of n equal minus infinity plus infinity of x of n e to the minus j omega n. Okay, and this again here is the definition of the DTFT of the original sequence. So this is x of e to the j omega with the DTFT, and so the delay corresponds, as I told before, as the shift of the phase shift e to the j omega n0. This is a pure phase shift times x, capital X of e to the j omega. Okay? Is it clear for everybody? Sorry, this is a bit of a mess. This is nothing to do. And the primo n è la stessa cosa. Yes, here n prime or n is the same thing. You can write n prime, you can write n is the same. Okay, let's see another property. Let's see the convolution of two sequences, and then this is the last of the properties that I will show you for today. Let's consider the convolution of two sequences, x of n equal to x of n convolved with y of n. Okay? And the convolution is, the definition of the convolution is similar as the continuous time convolution, but it's a summation instead of an integral. So we have summation of k equal to from minus infinity to plus infinity of x of k, y of n minus k. Okay? This is just the discrete time convolution. Now, if we want to compute the DTFT of z, we have that z of e to the j omega is equal to the definition summation for n that goes from minus infinity to plus infinity of z of n e to the minus j omega n. Okay? And if we substitute, we have that the summation on n of summation on k of x of k, y of n minus k times e to the minus j omega n. This is equal if we take the part that does not depend on n outside, the summation on k. We swap the two summation and we take the x of k outside of the first summation. So we have summation on n of y of n minus k e to the minus j omega n. Okay? Now, if we change again variable, we can write summation on k of x, sorry, of x of k, summation on, let's call it n prime, that goes from minus infinity to plus infinity, of y of n prime e to the minus j omega times n prime plus k, right? And again, we can split this e to the j omega n prime plus k, and we obtain summation on k of x of k, and the part on k we can take outside from the summation, so we have e to the minus j omega k, and the summation on n prime, or n if you prefer, it doesn't change, of y of n prime e to the minus j omega n prime. Okay? So what you see here, let's do it smaller. What you see here is the DFT, the DTFT of y of n, but here also we have the DTFT of x of n. So what we get basically is capital X of e to the j omega times capital Y of e to the j omega. And this is the proof that the convolution of the discrete time sequences gives us the multiplication of the DTFT. Okay? Is it clear for everybody? Are there any questions?
Yes, I do.
Yes, please. Are there any questions?
No, sir.
Okay. Okay, so the last thing that I want to show you today, let's go here, is the relationship between the Fourier transform and the discrete time Fourier transform that I skipped in the slides. And I skipped in the slide because I think it's easier that I show it here on the whiteboard than on the slides. It's probably easier to follow. Okay. So let's consider a continuous time signal, an analog signal, x a of t. Okay. And let's assume that has finite energy, so that has a Fourier transform of capital X, I would call it XA to distinguish it from the discrete time Fourier transform of the analog frequency FA. Okay. Now I write you the definition of the Fourier transform and this inverse Fourier transforms. This for easiness. So we have that this is equal to the integral from minus infinity to plus infinity of xa of t times e to the minus j 2 pi f a t in dt. And instead, the inverse Fourier transform is xa of t equal integral from minus infinity to plus infinity of capital XA of FA times e to the j 2 pi FAT in the FA. Okay, this is something that is known. Now, if we sample the signal with periodic sampling, so we have the sequence x of n that is originated by the sampling of xa of n capital T. This will be equal to integral of from minus infinity to plus infinity of xa of a of e j 2 pi f a n t in the FA. Okay, where I just substitute n capital T in this inverse Fourier transform equation here. Okay, but we can also consider xn, and we can also consider this as the result of the inverse discrete time Fourier transform. So basically, you can write this, but you can also write this as the the integral from minus 1/2 to plus 1/2, because we are using the frequency instead of the radian per second, the angular frequency of the dTft capital X of e with j 2 pi f. This is the dTft, well, this is the Fourier transform. So this is the dTft. And this one here is the Fourier transform in continuous time. Okay? So we have this multiplied by e j 2 pi and f in the f. Okay. Again, note that here we have the analog frequency, and here we have the frequency of the discrete time Fourier transform. These are not the same. Okay. So to make these two that are easy to compare, we substitute the variable of the analog frequency. So FA equal phi of A divided by T. Okay? And what we get is, so from this, what we get is 1 over T integral from minus infinity to plus infinity of xa of phi over T e to the j 2 pi n phi of A, and T they disappear together in the phi of A. Okay, and this will be equal to the integral from minus 1/2 to 1/2 of capital X of e to the j 2 pi f of e to the j 2 pi and f in the f. Okay. Now, if we look at this integral on the left, you can decompose this integral in sum of several integrals from -1/2 to 1/2. So basically what I'm saying is that you can split this in 1/t, 1/t summation for k that goes from -infinity to +infinity of the integral of k minus 1/2 and k plus 1/2 of x a phi of a over t divided by e j 2 pi n phi of a in the phi of a. Okay. I've lost the connection with the tablet. That's the problem, I think. Let's see. Let's see. Okay, now that should work. Okay. Okay, so basically what we're doing is that we are splitting this integral. This integral that goes from -infinity to +infinity to the summation, to connect, to the summation of to the summation of different integrals that goes from -1/2 to +1/2 plus k. Okay. I've lost again the connection of my tablet. Okay, just a second because I've lost the connection on the tablet. Okay, let me share again. Okay, let's see if it works. Otherwise, we have a problem. It should appear. Let's see. Let's go back on Teams. Okay, there it goes again. Okay, now you should see it again. So what I just said is that basically you are splitting this integral that goes from -infinity to +infinity in the summation of an integral that goes from -1/2 to +1/2 plus k. Okay, is it clear for everybody? And then what we can do, we can also change variable again. So we change variable instead of phi of a, we call it f plus k. So again, we change variable and we have that phi, oops. Basically what we get is that instead of phi of a, we use f plus k. Okay, and this we can use it now. frequency of the DTFT, because this frequency goes only from -1/2 to +1/2. And so what we obtain here is that 1/t summation on k of the integral that goes from -1/2 to 1/2 of capital XA of f plus k divided by t e to the j 2 pi n of f plus k in df. Okay. And so, since we have here the term of 2 pi, let me use a different color. Since we have here 2 pi times k, basically this can be ignored. This is periodic. So basically we can ignore the term in k. Okay, and we can write this as equal to, we can take the t and the summation inside the integral, and we have the integral from -1/2 to 1/2 of 1/t summation on k of XA of f plus k divided by t e to the j 2 pi and f in df. Okay. And so this is equal to the inverse discrete time Fourier transform, which, as you remember, maybe, it's equal to the integral from -1/2 to 1/2 of the capital X of e to the j 2 pi f e j 2 pi and f in df. Okay? So here we have immediately the relationship between the discrete time Fourier transform and the analog Fourier transform. Okay? So what we get is that the discrete time Fourier transform capital X of e to the j 2 pi f is equal to 1/t summation of k that goes from -infinity to +infinity of XA of f plus or minus is the same k divided by t. So we have that the DFT, apart from the factor 1/t here, is the periodic repetition of the Fourier transform. And this tells us that if the bandwidth of the analog signal, the bandwidth of the analog signal is limited, and if t is small enough, in particular, let's suppose that the band is B. If t is less than 1/2b, okay, then if the sampling period is small enough, smaller than 1/2b, then we can reconstruct the signal using a low pass filter, okay, without losing any information. And this is the sampling theorem that we have seen in the slides. Is it clear for everybody? Are there any questions? Okay, then let's, I think we can stop for today here. Let's see if there anything. Okay, yes, I think we can stop for today here. It's enough information. You can find most of the things that we have seen today in the lecture notes. I will upload the lecture notes of the other course in Italian, and I will also upload a translation that I've done a little bit quick and dirty, so don't expect a perfect English or perfect terminology, but at least it will be readable also in English. I hope that I will have the time to translate the lecture notes in English completely. Otherwise, you can use any automatic translator on the internet to get the information, and of course the proofs that I will give during the lectures. Next time we will see the other transforms that we have. The other transforms that we have that I talked about, the discrete time Fourier series and the discrete time, the discrete Fourier transform, and then we will go on from there. Okay. If you have problems translating the lecture notes, you can use the book from Professor Oppenheim. That's in English for sure. So in the worst case, there is always the book that you can use. Okay. Are there any questions? Any comments? Otherwise, I think that for today it's enough. At least I'm tired, so. Okay.
So kindly write down the name of the relevant book in the.
Can you speak louder? I cannot hear you very well.
Yes, sir. I am saying, kindly write down the name of relevant book which you refer.
The book I showed in the let me say this, in the Microsoft Teams you have the files. So if you go to the team, you have post where you have entered the meeting, but you have also files, and in the files I have made a directory called in Italian Materiale del Corso. I should change the name in material, course materials. There is no, okay, I don't know if I cannot rename it, but anyway, in this directory you have the slides from the last lecture with the name and information of the book, of the two books that I have suggested, and I have also uploaded the lecture notes from the Italian course. Okay. So I will also upload a translation that I've made for today's lecture, and you can use that one. I hope I will be able to translate the entire course, but I'm not sure. In the worst case, you can use the official book, and you have most of the things there as well. And I invite you also to follow the course and the mathematical proofs that I will give within. Okay. Are there any questions?
No, sir.
Any other question? Did you see the slides and the book? I mean the files that I have uploaded?
Yes, sir. I have found the file.
Okay, perfect.
I will translate them, and if there get any issue, then we will discuss in the next lecture.
Okay. If there are any problems or issues, just let me know. You can write me an email in any moment. Okay.
Sure, sir. Thank you.
Okay. Also, you can use. I will do this now. I will add here. I will show you what I'm doing so that you can see it. I will add another channel for you to talk to each other on this course. So let me share the entire screen. What I'm doing now is that I'm adding a channel in the digital signal processing course, and I will call it students channel. And you can use this to talk to each other, to ask questions and to exchange files or whatever you want. Okay, just write here to speak with the other students for any questions or any thing that that is not directly referred to me. Okay, in general, I don't use Microsoft Teams to communicate. I only use it for the meetings. Otherwise, write me an email because I don't look at my Microsoft Teams generally. It might take several days before I look at Microsoft Teams. So if the question is for me, write me an email. Otherwise, if you want to ask things to your fellow students, you can just write here in this students channel.
Oh, sure, sir.
Okay?
Okay.
In the students channel, usually I don't answer. I don't even look at it.
Okay, sir.
Okay. Are there any other questions? So if there are no other questions, then we can stop here for today. And we continue in 2 days on Thursday, 3 p.m. Okay, fine for everybody? So see you the day after tomorrow. Goodbye.